Okay. I'll begin by thanking the organizers for giving me the opportunity to present this work. The work is primarily a description of some developments in algorithms that can be used to study certain strongly constrained quantum models, namely the quantum timer model. The algorithm can be generalized to other models, but the results that I show here are for the quantum timer model. The work was done in collaboration with Bhupen and Fabienne from Toulouse. I'll basically describe the gist of the algorithm and the results that we get, the key results that we get from calculations using those algorithms. But the details of the scaling analysis and the particular quantities that we looked at can be found in this manuscript, which will soon appear in PRB. Just to give a broad overview of dimer model, Kedar had already given a description. Dimer model is a paradigmatic example of a strongly constrained model. It can be quantum or classical. The configurations of the dimer model can be thought of as living on a graph. In the work that I show here, it will be a square lattice, where you have some vertices and edges between some adjacent sites. The degrees of freedom, which are the dimers, live on the edges such that exactly one dimer touch every vertex. So this is an example of a configuration. And what we are studying is the thermal, the averages that come out of the thermal fluctuations in the set of configurations that are described by these constraints. The model was originally introduced in a somewhat chemical physics related context. However, it has been studied quite extensively in probabilistic combinatorics. Has been used to study physics of strongly constrained systems. It has been, as Kedar pointed out, there is a natural connection to RVB physics, fractionalization, and various frustrated spin models. I will not be talking about those, but I'll instead discuss the statistical physics and the algorithm aspects of these. The model has been also discussed, has been used to abstract constraints in Rydberg atom physics, and as Kedar's last talk described, it can be also used to understand aspects of localization in certain systems. So the classical dimer model has been studied quite extensively. In particular, the 2D classical dimer model. 2D classical dimer model is exactly solvable if the dimers do not have any additional interaction other than the constraints that we already described in the previous slide. So, which we'll call the non-interacting dimer model. If there are no other interactions, then the non-interacting dimer model can be related to a free fermion model in 2 dimensions, and various quantities like the dimer correlations, monomer correlations, etc., can be exactly solved in this case. The interacting dimer model can be defined. One way to define an simple interacting dimer model is to say that there is an energy cost of V when there is when a particular plaquette has two dimers in it. So it could be something like this or something like this. So the energy can be thought of as some constant times the total number of parallel dimers in the plaquette, either in the horizontal or the vertical direction. This interacting dimer model is not exactly solvable, but you can infer an effective description at high temperature in terms of a sine-Gordon model of a height field, in particular for the attractive case where there is an energy gain in having 2 parallel dimers, has been studied carefully in 2 dimensions. And numerically, you can show that the predictions from the effective description here is consistent with what you can get from careful numerical simulation, Monte Carlo simulation of the 2D classical diamond model. Here, the Coulomb gas constant G of the Sine-Gordon model can be thought of as a functional of the temperature, and you can, using exact simulations and comparing correlation functions, you can infer a G as a function of the temperature of the model. And also the coupling constants V. In the specific case of T going to infinity, the interactions are inconsequential, and therefore the model essentially behaves as if it's non-interacting. And in that case, from the exact solution, you can infer that comparing the correlations of this model with the exact solution, you can infer that the G is given by the Coulomb gas constant is given by half. Now, from the numerical simulations, you can use the winding number fluctuations, which I'll describe in a little more detail later, dimer-dimer correlations or monomer correlations using Monte Carlo simulations, and then infer G from there. As I mentioned, G goes to half as T goes to infinity, and G increases from half to 4 as T reduces from infinity to about 0.65, at which the leading order perturbations inside here, which where T is 4, becomes relevant, and you get a four-fold symmetry breaking into a columnar ordered phase. And in the region where between T equal to infinity and T equal to 0.65, you can estimate G, as I mentioned earlier. And this is the result of such a calculation. G essentially goes from 0.5 at T equal to infinity and reaches 4 close to the critical point. Now, the quantum dimer model is closely related to the classical dimer model. The Hilbert space is defined by the space formed by the orthonormal basis of classical dimer configurations. The Hamiltonian essentially is again related to the interacting dimer model. The potential energy is essentially the same as that in the classical dimer model. Energy cost associated with a parallel dimer with plaquettes containing a parallel dimer, which hereafter we'll call flippable plaquette, is given by some constant V. And then in the quantum model, you need a kinetic energy term, which essentially defines a tunneling between configurations that differ by a 90-degree flip of any specific flippable plaquette. For instance, if you have a large dimer configuration, if there is a specific plaquette which has a parallel dimer, and if you have a large dimer configuration, if that configuration differs from the other configuration only by a 90-degree rotation of a particular plaquette, then the K connects those two classical states, basis states, and we can set the coefficient, the constant to be 1. The Hamiltonian can then be written as the sum of all such terms over all plaquettes. What we are trying to infer is the finite temperature phase diagram of the quantum dimer model. And so what we will plot is V, the interaction or the potential V on the x-axis and temperature on the y-axis. We will set small letter t, which is the sort of the hopping term, to 1. In this version, with this choice, V equal to 1 corresponds to the case where you can exactly solve the ground state, which is the RK point. And if we consider the t going to infinity case, the interactions are the Hamiltonian is inconsequential, so you expect that the system will behave like a classical dimer model again, 2D classical dimer model again. So you'd expect that G will be half. So the infinite temperature system is likely to be described by G equal to half Sine-Gordon model. Now, in the on the left axis or left side of this figure, where V is essentially minus infinity or something like a large negative number, then the kinetic energy term is again inconsequential, and then we can again treat this as forming a classical 2D dimer model, and the vertical axis essentially is essentially describes the physics of aligning classical dimers on a square lattice, which we described a few moments ago. For that system, the critical temperature, as I mentioned, is 0.65. Below that critical temperature, there is a columnar order, and above that, there is a disordered phase. Now, if you go to the other end, when V is large positive, again, T, the kinetic energy term, can be ignored. And then again, I get a classical model. But here, there's an energy cost to having parallel dimers. So essentially, the dimers are sort of like repelling each other. This has also been studied carefully using Monte Carlo method. And as you can imagine, in the case of repulsive interaction between the dimers, you get a staggered phase at low temperatures and the disordered phase at the in the high temperature region. The critical temperature is known to be of the around 0.475 in units of V. Now, with these ingredients, you can construct the simplest phase diagram that you can think of. We don't know exactly what happens in this regime, but let's say we are not going to discuss this part. So let's focus on the region above some low temperature. Here we know that it's a columnar ordered system. Here we don't know exactly what the ordered phase is. Here we have a staggered phase at large positive V, but we don't know exactly what the ordered phase here is. But we can sort of expect that in the region above these phase transitions, you have some kind of Coulomb gas, Sine-Gordon model description, which again is likely to be described by a 2D effective model. And therefore, you can ask the question, what is the effective value of G, the Coulomb gas constant, in the scenario as you tune T and V in this critical phase? All right. So essentially, what we are, the use that we will put to our algorithms is to infer the effective value of G, how the effective G changes as a function of temperature and the interaction V. And the standard tool for studying such a system, finite temperature phases of such a system, would be the stochastic series expansion. I just gave you one slide, two-slide introduction to the stochastic series expansion. Essentially, you have this Hamiltonian. If I want the expectation value of some order parameter or some operator, for simplicity, let's assume it's a diagonal in the classical dimer basis. In that case, the expectation value, which can be written as trace of, which is proportional to trace of e to the power minus beta h times O, can be expanded this way, where I've basically expanded the exponential in orders of, in powers of beta h. If I assume that there is this series can be truncated at some large value of n, let me call that m, then you can do a little bit of algebra or some combinatorics and infer that the expectation value can be rewritten this way. Here, the summation psi over some d is essentially sum of all the classical dimer configurations. This essentially arises from the calculation of the trace, and the sum over, and the W that is being summed over here is essentially the sum of sum over a set of all operator sequences made up of Ki, Vi, and identity. And LW that is appearing here is essentially the length of the operator sequence that I have here. So, okay, now the precise details of this is not important. We just need to know that I have a sum over some kind of states, which are, essentially some direct product of the classical dimer configurations and operator strings, and you can define a probability. I can compare this equation to average over a probability distribution on these pairs, and that probability distribution has some specific form, which we can infer from this expression. And to compute the expectation value, I just need to average the operator O, which we assumed is diagonal in the dimer basis. And basically, I just need to sample those O from this distribution. Now, if I look at this quantity, the key quantity to pay attention to is the expectation value of an operator string between two classical dimer configurations. Now, psi has to be sampled from all classical dimer configuration, which itself satisfies strong constraints. And for if I pick a particular psi, then only certain operator sequences.
So you have to assume that O is an operator that doesn't couple different.
For simplicity, I've assumed that. That's not necessary. It's just that easier to explain it. Certain operator expectation values can be calculated even if it is not diagonal in the classical basis. Okay, sorry.
Yeah, sorry.
Okay, so so for a particular classical state psi, only certain operator strings will result in a non-zero expectation value, and there is a strong correlation between these two, and this is what makes an efficient sampling over this distribution very difficult. And to put it in a glib sense, the combination of constraints, the constraints essentially make it very difficult to get an efficient sampling of this probability distribution. A solution to this problem was sort of constructed by these authors in a paper in 2019, and they introduced what is called the sweeping cluster algorithm. And whatever I'm describing is essentially an extension of or improvement over whatever they have described. I'll give the rough idea of the algorithm and then discuss the idea of the improvement that we had made. And I'll also discuss what is the problem with the original algorithm. Okay, so I can think of this object, the expectation value, as some kind of a time evolution, and you have a state psi, and which is evolved into another state by the first entry of the operator string, which is evolved into another state by the second entry of the operator string, and then you have a set of time slices which are connected by the entries in the operator string here, W. So we can picture each choice of psi and W as some kind of, if you want a Feynman diagram of this kind. And if I ask what kind of operators appear inside W, you'll see that there are non-diagonal operators, which are the kinetic energy operators. Why? Because they scatter a state which has a dimer configuration like this to a state which has dimer configuration which is perpendicular, rotated, and therefore it scatters from one state to a different state. So it's the kinetic energy is non-diagonal in the classical basis. And then you have potential energy and identity operators which appear in these operator strings, and they are essentially diagonal. They can appear anywhere where the states in the time slice I and I+1 are identical. Okay, so we have this picture. Now the task is to sample through diagrams like this, essentially sample through states, classical states, and sample through some operator strings, operator sequences like N, D, etc. I've used N and D, but they essentially represent kinetic energy and essentially the potential energy operators, which are non-diagonal and diagonal respectively. Okay, so the easy part is to introduce diagonal operators, which are these operators. Essentially, wherever there is an existing identity operator, which essentially means that there is nothing between two time slices, you can insert a diagonal operator. And when you insert a diagonal operator, the statistical weight or the probability weight associated with this configuration changes, and you can decide the probability of or the rate at which a diagonal operator gets inserted using the change in the expectation value as you insert a diagonal operator into the string W. And you can construct the rate for the reverse process. Essentially, this kind of a process where I insert diagonal vertices or diagonal operators or remove diagonal operators essentially keeps the dimer configurations same because I'm just inserting some diagonal operators. It doesn't affect the non-diagonal operators, but essentially allows you to sample through configurations with different diagonal operator configurations. This is the harder part. Essentially, what to do to sample through the dimer configurations as well as interchange or sample between or have transitions between diagonal and non-diagonal operators. So I'll just give the basic idea without going into details. Essentially, I pick a random plaquette where there is a random flippable plaquette where there is either a diagonal or a non-diagonal plaquette. So if you have a diagonal plaquette, you can have two parallel dimers around it. If you have a non-diagonal plaquette, again, you can have two parallel dimers around it. It's just that in the non-diagonal case, they are rotated by 90 degrees. They're both flippable plaquettes. So I essentially pick one of these flippable plaquettes randomly and change the nature of the operator there. So I could take a previously non-diagonal plaquette here and replace it with the diagonal plaquette. And that means that there is a mismatch in the configuration on this slice versus the configuration on this slice. Essentially, that basically says that there is an instruction to change the dimer configuration as you go above. Essentially, you flip this again by 90 degree. The summary is that you can, after you initialize the system by converting a diagonal plaquette to a non-diagonal plaquette or a non-diagonal plaquette to a diagonal plaquette, you generate some update lines similar to the case in the stochastic series expansion. And these update lines move in the upward direction. And as it moves up, it flips the dimers that it sees in the plaquettes above along the path that it goes up. Whenever it encounters an operator, for instance, when it goes here, it encounters an operator. In that case, you can design some probable or rates for the operators to change from diagonal to non-diagonal or vice versa as these update lines move upwards. Some points that makes this algorithm complicated is that the update lines proliferate in number as you go upwards, and but it turns out that in practice, typically they vanish. The number of update lines vanish after several iterations. Upshot is that this kind of an update, this is just an example of a transition rate. This kind of an update where you create update lines which can go up and proliferate and then get annihilated later on. This allows you to efficiently sample between diagonal and non-diagonal plaquettes. Unfortunately, this is not ergodic because if you look at the winding numbers, again, I'll describe that in a moment, the winding numbers of these time slices, they can fluctuate wildly in the high temperature phase. However, when you implement this algorithm, it turns out it just doesn't fluctuate. Winding number essentially stays fixed. If you start with 0, it's always stuck at 0. So it's not ergodic. Then the question is there a way to make it ergodic? So just give a brief idea of the winding number. If I think of the dimer configuration, think of these as some examples of 3 dimer configurations. I have a fully columnar ordered system, a system which is differing from the columnar order by a few dimer flips, and a system where the dimer configuration has been changed from the columnar ordered state by an extensive change in the dimer configuration. It turns out that because of the constraints in the system, this model can be mapped to a model where there are fluxes going through the links, and the dimer constraint essentially boils down to conservation of flux in these models, in this picture. The precise details do not matter. Once you map it to a configuration of fluxes that are passing through the links, you can ask what is the total flux cutting through one, let's say, one vertical slice, and that essentially is the winding number. Yeah. So for instance, the total flux in this case is 0 because there are fluxes going forward and backward, and they're equal in number. In this case as well, that is true. In this case, there is a large flux going to the right, other fluxes are small, and they cancel each other, and then you get a winding number 1. Okay, so that is the picture in terms of flux, but I can rewrite that in terms of a simple quantity in the diamond configuration, original diamond configuration. These are, if you put a cut through any of the time slice, the number of, because it's a bipartite lattice, I can define odd and even link on each vertical slice. So odd, even, etc. And the number of dimers crossing the odd bonds along that cut minus the number of dimers crossing the even bonds along that cut essentially tells you the winding number. It just turns out to be equal to this up to some proportionality constant. Now, that's the rough idea. The way to solve the problem that the algorithm is not ergodic is to insert an equal time update in addition to the sweeping cluster update that I described earlier. Essentially, I consider a time slice. This is like a expectation value of psi, w psi that I showed earlier. I take a particular time slice here. I essentially do an update of the diamond configuration in that time slice. And if I blindly do that, it doesn't work because there are constraints that are imposed by the operators above. Essentially, the dimers that are in a plaquette that contains a non-diagonal plaquette cannot be changed, so that puts a hard constraint on how I can sample each layer. Dimers away from the non-diagonal plaquettes are not strongly constrained, and they are the same across all time slices. So essentially, what we do is take a particular time slice wherever there is a non-diagonal plaquette, which are shown in green here. I freeze all the dimers there. And for the other regions, I define an effective classical model, which takes into account the number of diagonal plaquettes that are above that plaquette. So essentially, I can define an effective classical model, and this effective there are efficient algorithms to sample configurations in a classical model, irrespective of how complicated the interaction is. Therefore, by defining an effective classical model, by putting a constraint on non-diagonal plaquettes and defining an effective interaction between plaquettes to take into account the existence of diagonal plaquettes in the tower, we can sample the configuration in each time slice. Essentially, this allows winding number fluctuations, and the algorithm is then ergodic, we hope. However, it fails again when there are too many diagonal plaquettes, non-diagonal operator vertices, which essentially happens at low temperature, which is why I said that we cannot say anything reliably at low temperatures. However, it works extremely well at high temperatures, and and now I'll describe the results that we get from using these algorithms. The phase diagram that we get can be summarized here. Again, I should not take the points very close to 0 temperature too seriously. They are just extensions of the lines that we got from above. So we can calculate the winding number fluctuations, and in the columnar order phase using the algorithm that I described just now. And you can see that as the interaction goes from strongly attractive dimers to repulsive dimers, the winding number increases. And you can calculate, you can calculate the winding number fluctuations. You can relate the winding number fluctuations to the height field model, the Sine-Gordon model, where you have the relation between the winding number fluctuations and the Coulomb gas constant. You can invert this relation numerically or otherwise and get G from the estimated winding number fluctuations. And we can essentially estimate the lines of constant G using this calculation, and these are the lines that we get. As you go to attractive interaction, the G increases, it keeps increasing and reaches some point where G becomes 4, and then it goes into some kind of a columnar ordered phase. And in the other direction, G decreases and the winding number increases, and when G hits 0, the system goes into staggered phase. Yeah. Okay. Now, we did calculations with system sizes up from 24 to 48, and there is barely any, so there are many lines overlapping here. Different lines indicate the winding number fluctuations for different V values, so these ones, and on each line there are calculations done for different system sizes. They're overlapping, which is essentially saying that there is hardly any finite size effect for some reason, and we can reliably estimate the values of G from the winding number fluctuations. You can also independently calculate scaling exponents of dimer-dimer correlations and monomer correlations. They have slightly more finite size effects, and the results essentially agree with this to a good approximation. Okay, we can estimate the line of columnar ordering transition. We can use the Bindra-Quimelen crossing for rotational symmetry breaking order parameter. We could use the difference between the vertical and horizontal dimers, and the Bindra-Quimelen crossing point for that essentially can be used to estimate this. You can also use the rotational symmetry breaking, fourfold rotational symmetry breaking order parameter, which is cosine 4 theta. Theta is the angle of the average columnar order parameter. On the staggered side, again, you can estimate the transition temperatures by using a Bindra-Quimelen for a quantity that looks like modulus of Wx plus Wy. Essentially, the idea is that in the staggered phase, the fluxes have extremely large values, so the average value of this diverges across the staggered phase transition. So that can be sort of seen in the Bindra-Quimelen for that quantity. Okay. Now we get these phase diagrams with the constant G lines mapped on it, and to do a sanity check, you can do a simple high temperature small v expansion for the partition function for the quantum dimer model, and we can get an estimate of G, which is valid in high T small v region, and we can conclude that these green lines essentially correspond to the estimates from the high T expansion, and these constant G lines exactly match with what you expect from the high T expansion. Okay. In particular, at least I found this appealing that the G equal to half line, which should correspond to the non-interacting dimer model, at T equal to infinity, it essentially goes vertically and it bends sideways and looks like it reaches the RK point at low temperature. And for values of interaction that are to the right of this G equal to half line, you get a strange kind of a reentrant behavior as you go upwards in temperature. Okay, so I finished on time. Essentially, we have devised an efficient Monte Carlo algorithm that can be used to estimate properties of the quantum dimer model at high temperatures. It essentially is an extension of the sweeping cluster algorithm. It can reliably estimate winding number fluctuations, dimer correlations, and monomer correlations in the high temperature phase, and the computed G, the map of G, essentially is consistent across different ways of estimating G, and we could reliably check that there is not a significant finite size effect, at least going from n equal to 24 to 48. The interesting problem would have been to extend this algorithm down to the lowest temperature. The essential difficulty is that in the algorithm, we freeze the dimers that are sitting below non-diagonal plaquettes. And so once they are frozen, there can be no equal time update that I mentioned earlier. And as you go to low temperature, the number of non-diagonal plaquettes proliferate, and therefore the algorithm fails. Okay, so there are more details in this archive preprint, but it should appear in PRB soon. Okay.
Thank you very much for this very nice talk. We have time for a couple of, even more questions. So, any question? Yes, Bhaskar, please.
Sreejit, nice talk. Suppose I want to understand it in terms of condensation of excitations. Because RK point corresponds to gap plus Z2 excitation, Weissan excitations. So when you go away, they get gap.
Yeah.
So is there a way of analytical understanding of whatever you are getting numerically?
I don't think so, because the physics close to the RK point is qualitatively different from what we get at high temperatures.
But I'm saying in the low temperature region.
Oh, in the low temperature region are these, oops, why doesn't it?
Go to your phase diagram.
Yeah, yeah. So the phase diagram that we get in this region is just an extrapolation of what we get at high temperature.
So it's supposed to be Weissan gap.
Presumably, I do not know, but the algorithm cannot be relied upon in this region. Whatever lines we have drawn towards the RK point are just extrapolations of the lines that we get at high temperatures. Even this phase transition line from the disordered phase to the ordered phase here, that line is merely extrapolated. It looks nicely going towards the RK point, but I wouldn't use the algorithm to infer anything in this region. So I don't think we should be able to say anything about the Weissan gap from here.
Thank you.
Any further questions?
Hi, can I ask a question?
Sure.
Yeah. So hi, Sreejit, this is Arnab here. So you mentioned that this algorithm becomes inefficient near the RK point if you go to low temperatures. So is the essential reason that somehow the winding numbers which fluctuate a lot in the neighborhood of the RK point, your algorithm cannot sort of incorporate those fluctuations?
That could be one way to think about it. Okay, let me say that empirically what we find is that the autocorrelation time goes up, but in a sense why the improved algorithm also fails can be understood. Oops. Yeah, so the original algorithm with just the sweeping cluster update fails for the reason that the height of the tower goes up. The M that I described, the cutoff length goes up, and the sweeping cluster update becomes inefficient. Even this algorithm becomes inefficient because once the height of this tower goes to very large values, almost every plaquette here will have some non-diagonal plaquette somewhere in the tower, which means that because of the constraint I mentioned here, I have to freeze almost every dimers, and there is no more equal time update that I can do. Therefore, therefore this equal time update just doesn't run at low temperature, not just near the RK point, at low temperatures throughout. I don't know if that partly answers your question.
Okay, thanks.
There is an alternate algorithm that was suggested by the authors of the original paper, where they did a directed loop algorithm in the layer and then created update lines starting from those. It just doesn't work again.
Any more questions, either online? I can't see the online participants on this screen, maybe on some other screen. So
Online questions come from the sky.
they come from the sky, exactly, the voice. Maybe I have a question. So you did the simulation for the bipartite square lattice. I think this is, you never used the bipartite lattice.
The winding number fluctuation.
Right, okay. So it means that would prevent you to do calculations, for example, on the triangular lattice?
The algorithm works fine on the triangular lattice. It's just that we have not studied it.
All right, but then it would be difficult to extract some effective G. Or
Well, there is no critical phase.
it's not critical.
So there is no G that you can estimate at high temperatures. But algorithm should work fine even on a triangular lattice. It should work on even other constrained models like some ring exchange bosonic models,
Right.
some fermionic models also.
Right. Okay, so if I don't see any more raised hands. So thank you very much for the talk.